गुड मॉर्निंग सभी को मेरा नमस्कार। आज हम 53rd एपिसोड कर रहे हैं। पता नहीं चल रहा कि हमारी 50 हाफ सेंचुरी कब पूरी हो गई। मतलब इतने एक्साइटिंग एपिसोड थे कि सभी को बहुत मज़ा आ गया और हमें भी बहुत आपके साथ काम करते समय बहुत मज़ा आ गया। टुडे एज आई मेंशन यू 53rd एपिसोड कुछ स्पेशल टॉपिक भी होना चाहिए। तो टुडे वी आर डूइंग द एपिसोड ऑन अनरावलिंग द यूनिवर्स विद द जेम्स वेब स्पेस टेलीस्कोप। आज हम जेम्स वेब स्पेस टेलीस्कोप के बारे में ज़्यादा जानने वाले हैं। तो बिफोर दैट आई वुड लाइक टू गिव द tour of the ISER Pune. So I'm showing you, so this is a building of the ISER Pune. Here we do lot of outreach activity for students and the teachers. And in this campus we have various departments including our science activity center. But before that I would like to show you the quote at the entrance of our main building, the ISER Pune, where tomorrow's science begins today. Why I am showing this quote you again and again? Because this quote is very appropriate for our series. Now I am showing you the science activity center at the ISER Pune. Here we do lot of outreach activity. We conduct workshop for students, workshop for the teachers. Just see the glimpse of the one of our workshop and you can see the faces, happy faces of the children, and see the spark in their eyes. They are so happy when we explain them various concepts of science and mathematics using hands-on activities. We also conduct lot of workshop for the teacher. So this is one of the teachers workshop. Now let's move towards today's topic. As I mentioned you, the name of the today's topic is very interesting. Unraveling the universe with James Webb Space Telescope. And today we have invited Dr. Varun Bhalerao to give you talk on this particular topic. Now let me introduce Varun. Dr. Varun Bhalerao obtained his BTech degree in electrical engineering from IIT Bombay, followed by his PhD degree from Caltech in 2012. Presently, Varun is an astrophysicist at IIT Bombay. He and his group are working on the development of Growth India. This is India's first fully robotic telescope. His group also studying to find the gravitational wave sources. Varun has received many awards. Varun is a recipient of the Venu Bapu Gold Medal, the highest honor given in the Astronomical Society of the India. He is also associate of Indian Academy of Sciences and recipient of the DST Inspire Faculty Fellowship. Now, without any further delay, I am requesting Varun, please start your today's session on James Webb Space Telescope. Over to you, Varun.
Thank you very much for that very warm introduction. I'm very happy to be here talking to all of you on this Sunday lecture series. I'm Varun Bhalerao. I'm a scientist at the Indian Institute of Technology, Bombay. And today we are going to chat about the James Webb Space Telescope. So this is the latest space telescope that has been touted as something that will actually show us the farthest and the earliest secrets of the universe that we have not been able to see so far. So let's start. In a nutshell, what is James Webb Space Telescope, also simply known as the JWST? So here's what it is. The James Webb Space Telescope is a large infrared space telescope orbiting L2 at a large distance from the Earth, helping us study the earliest galaxies, evolution of galaxies, birth of stars, and to look for building blocks of life in planets around other stars. Now, this feels like a textbook definition, right? This is a very long and complicated sentence, but this is really what it is in a nutshell. And what we are going to do over the next hour or so is take this sentence and break it down piece by piece and try to understand what JWST really is. So, first and foremost, it is a telescope. So, why do astronomers care about telescopes? I'm sure you may have heard about telescopes somewhere or the other, and typically we attribute telescopes to Galileo. But actually, Galileo was not the inventor of the telescope. They were invented by this guy known as Hans Lippershey. And what Galileo did, though, was he actually improved their quality and started systematically using them for astronomy. He wasn't even the first person to use them. So here is Galileo's telescope. He wasn't the first one to take a telescope and just point it to the sky. But what set him apart was that he started doing it scientifically and methodically. So he had this telescope, he improved its quality, made better ones, and with those telescopes, he started looking at the sky extremely systematically. Now, this telescope for that time was revolutionary. It had 30 times the magnification of the human eye. And what that did is actually it let Galileo make a lot of new discoveries. So here are some sketches by Galileo, and he was the first person to realize that the moon was not actually a perfect smooth sphere. The moon actually had mountains and valleys and bumps and so on. He also discovered that the sun actually has spots. Now, this is where Galileo actually got a bit lucky by his telescope not being very good. Do not point a telescope to the sun, it will burn your eyes. Okay. He also discovered that the Venus has phases, just like you have phases of the moon, half moon and a crescent moon and a gibbous moon and so on. Venus also has phases. And he also saw moons around Jupiter. This was the first time ever that there was evidence of something orbiting something other than the sun. And at that point, actually, remember, we are talking about ancient history. So all of our understanding of the solar system, about the place of the sun, the place of the earth, what orbits what, and so on, these things were not at all clear. And at the same time, his telescope did have limitations. He noted that Saturn has bumps. What do you mean by bumps? Well, today we all know that Saturn has rings. So you take Saturn and you have rings around it, but his telescope was not good enough to actually show the rings distinctly. So they appeared very blurred, as if you were squinting and looking at them. And because of that, he just saw them as extensions around the center of Saturn at two sides. Okay, so this was a big leap with Galileo's telescopes, but Galileo's telescope by modern times is a very small thing. In the coming back to this definition, I said that this telescope is a large infrared space telescope. So let's put that into perspective. Let's look at how large is large, and then of course, why do we care about large? Okay, so here is Galileo's telescope. So on my screen right now in front of me, if you're viewing this on a typical laptop, then this circle is about 37 millimeters in diameter. That was the size of the lens of Galileo's telescope. Okay, if you today go out to say your local amateur astronomy club, if there's someone holding a stargazing session, then a common one is a 3-inch refractor. So the main lens is about 3 inches in diameter. If you go to more powerful ones, so when I started learning astronomy seriously, in Pune, Ayuka used to conduct telescope making sessions, and I built what I was very proud of was a 6-inch telescope, and it also had a mirror instead of a lens. Okay, so that's about 15 centimeters in diameter for the primary mirror. Now, when I have become a professional astronomer, this 6-inch reflector is also not large enough. To put it in perspective, we now use something called the Growth India telescope in Ladakh. So this is the telescope. It sits at this beautiful location on Mount Saraswati in Ladakh. And the primary mirror of this telescope, which sits here, so light comes in from this side, gets reflected from the primary to the secondary by another mirror and goes into this camera here. So this is a 70 centimeter mirror. And in comparison, this is my 6-inch telescope, and the size of this laser dot that you are seeing is roughly the size of Galileo's telescope. Much, much, much smaller than the research telescopes we use now. So how does this Growth India telescope compare with other telescopes around the world? Well, even within India, this is actually among the most small research class telescopes. Okay, the largest one we have is more than 3 meters, 3.6 meters in diameter now. Right? And why do we want these large? So here's a simple experiment I'm sure you'll have done at some point or the other. If you have a large lens, for example, here is someone holding a lens to the sun, it focuses light, you get more light onto that small point. So in direct sunlight, a match would not have caught fire. But the moment you use a magnifying glass and point it here, what is going to happen is that all the sunlight is getting focused at this small point, and the temperature is becoming so large because all the light is coming together. So we want to do the same idea. If we are wanting to look at faint objects, then a large lens or a large mirror will actually collect that much more light for us into a small space, which means that it will actually make those things appear brighter so that we will be able to see them. Okay, so here is Growth India telescope again, and here are the world's largest telescopes. That makes Growth India look a bit too large. Here is actually it scaled to size. So remember now, Galileo's telescope on this point will be smaller than a pixel. The largest operational telescopes right now are 10-meter class telescopes. For example, these are the Keck telescopes. There's the Southern Australian Large Telescope over here. These are mirrors which are 10 meters in diameter. Future telescopes which are coming up, India is a partner in the 30-meter telescope, which, as the name suggests, this thing will be 30 meters. That's about as much as a 10-floor building, by the way. And down here is James Webb Space Telescope with a mirror whose diameter is 6.5 meters. Okay, 6.5 meters again is about more than 2 floors tall. So this is going to allow us to see things which are much, much fainter than what can be seen by our eyes. The diameter of our pupil is less than a centimeter, so we can see only much brighter things. The other reason why we want to go for a large telescope is something called resolution, or very loosely put, the sharpness of an image. Okay, so this is an image I took from the balcony of my house using a phone's camera. Okay, and with this camera, in this picture, there is a nice kingfisher sitting right here. Okay, can you see it? It is in this circle. Well, obviously you can't. So let me take that box and let me zoom in, and you still cannot see the bird, right? Where is the bird in this image? So what I did though was I switched to another instrument, and now you can see the bird. This is a picture taken of the net, but this was now visible right at this point. So let's go back to this picture. At this point in this image, we have this bird sitting. So how did I manage to see it? Well, this circle can actually give you a clue. What I did was I took binoculars and I put my phone camera behind that. Now my phone's camera lens is something which is just about this size, but the binoculars lens is much larger. Okay, suppose it is about 10 times larger, it gives me a 10 times sharper image. This is called resolution, and going to the larger telescope actually gives us much better resolution, much sharper pictures, so we can understand those objects much, much better. So larger aperture, more clarity, more light, and hence we go for the large size. So it's a large telescope, but it is also, there's one more word here, it's an infrared telescope. So what is infrared? Well, light is made of electromagnetic waves. If you look at something like the FM radio waves that you're using, the microwaves that you use to heat food, X-rays that are used by doctors in hospitals, optical light, infrared, which we typically call heat, they are all forms of light. And what is shown here is the wavelength of these and what is the physical size scale of things there, which would compare to that wavelength. But you can also think of light in terms of frequency and so on. So infrared is just longer wavelengths of light as compared to visible. Okay, this is often known as heat vision. You will have seen this probably in recent days when at some installations during the pandemic, they had these cameras which showed you a heat vision and allowed the camera could see who had fever. So here are two images. I am standing here taking a picture, and you can see a red cap here which is appearing blue because blue is representing colder things. So here you see a hat, and in the infrared image you see two hot spots here. That is where this person's head is actually touching the hat, so it's hotter than the rest of it. Okay, similarly here you see something quite interesting. This lady is wearing glasses, okay, but the glass itself is not transparent to infrared light. So those parts appear cool, whereas the rest of her face is appearing warm. So when you see something at a new wavelength, you understand something else by using a different type of light that was not clear from your optical visible light. It also has other uses. Infrared, optical is very easily blocked by gas or dust, whereas infrared can actually pass through that. So here is an example with an optical camera. This is a firefighter going into a smoke-filled room. He cannot see anything, but when you switch on the infrared camera, then you can actually see there's a person who's lying down here unconscious. Thanks to this camera, the firefighter will see this person and they can go and rescue them. So infrared passes through stuff. This is very important when we are looking at, say, the early universe. If we are trying to study the formation of galaxies, there's a lot of dust and gas that would have blocked optical light. If you have seen images of the Milky Way galaxy itself, you see a dark band, or if you have been fortunate enough to go to a very dark site, you'll actually see that the Milky Way has a dark band through the center. That is a sight definitely worth seeing. If you have not yet been to a dark enough sky, I would very strongly encourage that you do so. So that dark band again comes from gas and dust in the plane of the Milky Way. If you look at it in infrared, you can see straight through it. Okay, so if you want to study these kind of things, then the next generation telescope should observe in infrared. There is also one more factor. Okay, there is something called a cosmological redshift. So I have Earth here, and on this side I'm showing a galaxy which is, say, 4 billion light years away. What it means is that the light that is reaching us today was emitted by that galaxy 4 billion years ago. Okay, and because of this, there's an interesting fact that we have to consider. 4 billion years ago, the galaxy and Earth were actually both closer to each other. The universe, you may have heard about the Big Bang theory. About 13 billion years ago, the universe was born in a Big Bang, and it has been expanding ever since. So 4 billion years ago, the galaxy was actually closer to us. Let us imagine that it emitted green light, which has a wavelength of, say, 500 nanometers. Now, you're used to thinking about meters. Millimeter is 1,000th of a meter. A micrometer or a micron is 1,000 times smaller, and nanometer is 1,000 times smaller than that. So this is about 0.5 microns wavelength of light. So this galaxy emits green light at 500 nanometers. Say 2 billion years ago, the universe had expanded. What does it mean that the universe expanded? Everything in it expanded. So this light itself also got stretched, and its frequency, its wavelength, which used to be 500 nanometers, now have been stretched to maybe 590 nanometers, which we would call yellow light. So the light when it was emitted was green, now it's become yellow. And today when it reaches us, okay, it's going to look red. So if I want to study something in optical, but it is very far away, it means that I'm looking at it through a large cosmological redshift, and that optical light will not appear as optical. This sounds a bit confusing, so let us look at it again. Okay, typical stars emit all the way from ultraviolet light to optical to infrared. It depends on the temperature. The sun's emission, for example, peaks in optical. But in general, below about 91 nanometers, the universe becomes opaque. That is when the frequency is high enough that you start ionizing hydrogen and so on. We won't go into those details. But below 91 nanometers, the universe is opaque. Now, suppose I want to study something that's very far away. Say we measure this in terms of redshift, in terms of this, how much has the wavelength of light changed? So 500 nanometers becoming 675 nanometers would be, you can calculate the redshift based on the change of wavelength. Okay, and instead of that, now if I look at, say, redshift 20, which is what James Webb Space Telescope wants to look at, then this 91 nanometer light would actually reach JWST as infrared light. So this is far ultraviolet light, but at such a high redshift, it actually becomes 1.9 microns. It becomes infrared light. Or if I take optical light, so if there was a star, sun-like star, say, emitting an optical, then at redshift 20, that light now will get shifted all the way to 10 microns. Okay, the range for which James Webb Space Telescope has been built is about 0.6 microns. That's around red light to 28.5 microns, so that it covers this entire range and can study stars, galaxies, planets, and everything in those wavelength ranges. So that tells us why it is infrared, but then why does it have to be a space telescope? Why can't you just do it on the ground? That's so much easier. Well, the atmosphere does a bunch of things. Okay, so what is plotted here on the x-axis again is wavelength. So we have X-rays and gamma rays here. This rainbow here shows optical light, and then there are radio waves and so on. And what you see is that optical light makes it all the way down, only about 10% is absorbed. Radio nicely makes it all the way to the ground, but high energy radiation and infrared radiation are blocked by the atmosphere. This actually is great for us. This means that the ozone layer, for example, and other components of the atmosphere are blocking all the UV light and the X-rays and the gamma rays that are coming from the sun, which was important for life to evolve to begin with, because otherwise our cells would start disintegrating under all of that radiation. But if you want to study the universe in infrared, this is bad news, because none of that infrared light is actually making it to space. Okay, remember, we are looking at this kind of wavelength range. Some of it maybe we could have studied from the ground, but this middle infrared, far infrared range is getting completely blocked. But that's not the only problem. The other issue that the atmosphere does is this twinkling. So what is shown here is, we are all familiar with twinkling, right? You go to a nice location and you see stars apparently changing in brightness. What is really happening, so let me play this again, is that the image of the star is shifting, jumping around, and changing in brightness. So this is a very high speed movie taken of a star called Betelgeuse. It's part of Orion or Mriga Nakshatra. If you look at it with a large telescope and take high speed images, you see the images jumping all over. Now, the 4.2-meter telescope actually has enough clarity that the star's size should have been about this much, okay, the size of this spot. But all of this mess and all of this jumping around has been caused by our atmosphere. So you don't want to have that problem. And the solution is to get rid of the atmosphere. Well, we like to live, we like to have oxygen, so we can't just eliminate Earth's atmosphere. Instead of that, you launch a telescope into space. Okay. So this is not the first space telescope. AstroSat is India's very own space telescope. You see a model of AstroSat behind me right here. You can look up more information about it. Last week, you may have heard about AstroSat discovering its 500th gamma ray burst. So this is the instrument, cadmium zinc telluride imager, which actually discovered all these bursts, which are the instants where black holes are born. So we have our own space telescopes too. There are more coming up, Aditya L1, then there is Polix and the ExpoSat mission and other proposed missions that we have. For example, this is another satellite we are working on. It's a proposed mission called Daksha. So yes, space telescopes have become common. They're ultra cool, and they enable us to do a lot of science that would not have been possible from the ground. Let's come back to James Webb Space Telescope. So the space telescope is not orbiting Earth, but it is orbiting L2 at a large distance from Earth. So what is this business now? Well, we usually think of space as cold, but low Earth orbit can be very, very hot. So I just told you about this mission called Daksha. So we were doing calculations of how hot this will be if it is orbiting around Earth in what is called a low Earth orbit. So about 600, 700 kilometers above Earth, which is where a lot of the satellites are. So when we did these calculations, and you just got a glimpse of Daksha, here it is. So when we did these calculations, the maximum temperature actually was going to 78 degrees Celsius, and the minimum temperature was going to only about 18 degrees Celsius in our early calculations. Later, of course, we have refined this and made this cooler, but this thing is really hot. Now, a problem with this is that hot objects emit heat, and that is infrared radiation. Okay, to give you more examples, if you take the moon, the side of the moon which faces the Earth is the sun is 130 degrees Celsius, but the other side, which is in shadow, is at minus 170. That's a huge variation. And if you're in low Earth orbit, you have heat from the Earth and heat from the sun, and that's a lot of heat that you have to deal with. That is going to mess up your observations. It's as if you are trying to look at something faint and someone is shining a torch into your eyes. You really don't want that to happen, right? Well, you go far from the Earth, but it's hard to get far away from the sun. So the solution is that we just want to block the sunlight. Okay, and one place where we can block the Earth and block the sun nicely is this point called L2, Lagrange point. Okay, so this blue circle here shows the orbit of the Earth. This is the orbit of the moon around Earth. This is not to scale, but there's a point here where the gravity of Earth plus gravity of sun is exactly cancelled out by the centrifugal force by moving in this orbit. Okay, and that is where we have James Webb Space Telescope. It is not sitting just at the L2 point. It actually has an orbit around the L2 point for detailed physics reasons, which we don't won't go into today. But if you are inclined so, then look it up. There are some links I'll give on the last slide where they explain how the orbit is, why it is stable, and so on. Okay, and what is done here, you can see, is that James Webb Space Telescope has this diamond-shaped thing behind it. This is the telescope mirror, and this is called a sun shield, which is blocking the sun and the earth as seen by the telescope. So all of that heat is lost, and we'll talk more about that soon. So why does all of this blocking matter? Well, let's get an idea. Flux is the intensity, the amount of light or energy we are receiving from a source. So sun, earth, and even the telescope itself is going to emit infrared. So how much does it emit? Well, a far away galaxy of the sort that JWST is going to be used to study emits flux of 9 nanojansky. Okay, Jansky is a unit of radiation. Let's not worry about the details. Let's just remember this number, nanojansky. Okay. Now, if a person were standing in front of James Webb Space Telescope, maybe operating something, okay, in the same units of nanojansky, this is how much the flux of that person would be. So this person would emit a million into 1.9 lakh. So 2 lakh million times as much radiation as that distant galaxy. You're not going to see that galaxy, right? This is like a firefly in front of the sun. On the other hand, if you are far away from Earth, well, no people around, that's good, but the Earth is still very bright. Okay, this is the radiation, the intensity of Earth. So this is 10 million nanojansky is what the Earth would emit. So to get rid of all of these radiation, they use these highly reflective sun shields. So what do these sun shields do? Well, the telescope is sitting on this side. There are sun shields here. Sunlight and light of the Earth comes onto this side. The outer layer reflects out most of the light, and it gets quite hot. It gets up to 125 degrees Celsius. But then there are successive layers which are reflecting some part of the heat that goes through, that is reflected by the next layer, and next layer, and next layer, and so on. And finally, the innermost layer that is on the telescope side is at minus 235 degrees Celsius. Right? That is what we mean by space is cold. If you're blocking out sunlight, then you can do great. So this is ultra cold. Of course, that means a lot of engineering challenges had to be met to make something work at this temperature. To give you a story about Ladakh, the telescope that I showed you, Growth India telescope, Ladakh in winter can get very cold, easily drops below minus 20 degrees Celsius. The normal grease that you use for bearings or say oiling your bicycle, that grease freezes at those temperatures and the telescope would get jammed. So even there we have to take special precautions. But instead of minus 20, here we are talking about minus 235 degrees Celsius. Lots of engineering challenges that came up there. Okay, and here is now the first perspective of James Webb Space Telescope. You see these people, how small they are in comparison to the shield. The area of this sun shield itself, just the top layer, is 1500 square feet almost. So that is the size of a house, okay, or a largish house probably. So that is how large these shields are, and that now starts to give you some perspective about the size of this telescope. So to recap, what would you want the next generation telescope to be like? Well, you want it to be a big telescope, but then you want to fit it inside a rocket, take it all the way to L2, keep it very, very cool. And then, of course, because it is very far away from Earth, you are not going to be able to, array, wire loose ho gaya, let me tighten that. Oh, let me move the mirror slightly. That's not a possibility. So you want it to be extremely robust and reliable. How do you do that? Well, that is exactly what the big team behind James Webb Space Telescope did while putting it together. Okay, and I'll now walk you through some of those solutions. So here's the size comparison. This is a 3-floor building. This is from here to here, 6.5 meters. It is composed of these hexagonal segments, which will come at, and it's about the size of a tennis court. Okay. So here are the mirrors. This individual mirror segment from here to here, from one flat edge to the opposite flat edge, is about 1.3 meters in diameter. Making a single 6.5 meter mirror is very difficult and had other problems associated with it, which is why the mirror was made in these segments. And this total diameter makes it the largest space telescope ever launched at 6.5 meters. Here are various testing images and videos at various stages of the mirror, and you'll notice that these side things have actually been folded. That is because this entire telescope has to fit inside the nose cone of a rocket at the time of launch, and we'll see that in a moment. So here is the rocket. Again, to give you perspective, this is about 15 floors tall. So we are just going up in an elevator as this video is being taken. Still going up, still going up. So James Webb itself, remember, is very big, but this again gives you a perspective of how large the rocket is. And the nose cone is too small. Now, nose cone is again this area where this is mounted. This is about 250 square feet. Now, I'm in Mumbai. In Mumbai, that is also the size of a house. Okay. But this is still the unfolded telescope would be way too large, which is why the telescope actually had to be folded in origami style. And then once it went to space, it actually opened up and deployed, got the full sun shield in order, got the mirrors in order, and so on. Okay, so this was launched. Of course, nothing is complete without watching a launch video. So here you have the massive Ariane 5 rocket. Let's have some countdowns here.
And liftoff.
And there you have it.
Decollage,
So
liftoff
this
from a
was
tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
all right. And then once it was launched in orbit, here is what happened next. So this is the last shot that we saw of JWST. As it was released from the rocket, you can see Earth at the bottom here. In these, you can actually see reflection of the rocket. You can see these jet plumes over here, which is thrusters that are aligning the last stage of the rocket itself. So this shot had become quite famous as the last view of James Webb Space Telescope. I've put it in quotes because it is not actually quite the last. You also saw some small pieces fly off over there, and the rocket is firing small thrusters. You can see the reflection here again to align itself so that it can keep taking these videos. Now, up to this point, instruments on the James Webb Space Telescope were being powered from batteries on the rocket. But now that that is done, the first thing that you have to do is make sure that you have power to continue operating. So as soon as it was at a safe distance from the rocket, the first thing that JWST did was that it deployed its solar panels so that it can continue functioning. And we will see that around now. Oops. Let's go back and see that. So yes, there you are, solar panels getting deployed. Notice how the solar panels themselves are going to become quite large, but they've been very nicely folded into an extremely compact formation. And with this, at this point, basically, it became a self-sustaining satellite, a complete spacecraft that no longer depended on anything outside of it. So with that farewell view of James Webb, let's move on. So here are the operations that then happened after that. Let's get rid of the music here. So the first thing that it did, which we just saw, was that it deployed its solar panels. A little bit after that, one orbit after that to be precise, it deployed an antenna over here, which is what allowed it to communicate to Earth. Then the sun shield itself had been nicely folded in. That got opened and moved out of the way. The telescope then had to be raised away from the structure so that the structure could be deployed safely. This is something which is quite interesting for people who are interested in the details. It allows the telescope, the momentum flap, to maintain its orientation. And now you have these telescopic booms coming out one side at a time. You want to be very careful. You don't want to jerk this open by trying too many things in one shot. So one side deployed first, then the other side, and with wires pulling things out. There is a thin wire here which is pulling the shield out after the boom. And once these were deployed, they actually were stretched out and separated. So those layers now became separate layers. And then after all of that was done, the main secondary mirror was brought into place. And finally, these side mirrors were opened so that, oh, sorry, I forgot the radiator plate. This is again for cooling things down. And then finally, the full mirror became one shape. So this was all done in a period of about 2 weeks after launch. And that is what gave JWST its final structure. And then around a month after launch, it was injected into its final orbit by firing thrusters to correct its orbit. Okay, so what happened after that? Well, first thing that happened was that it was at room temperature. It had to start cooling down. So it took a very long time. There is cooling something down is very difficult. Okay, this is something you kind of experience at home. You take water, you put it on the stove, you can heat it up within a few minutes. But to bring it down again, you can add ice, but there's no ice that's going to take you to minus 235 degrees Celsius. So you just have to wait for it to slowly cool and cool and cool and cool. Okay, so about a month later, when it reached a temperature of 120 Kelvin, that's about minus 150 degrees Celsius, the first near infrared camera, NIR cam, started operating. After that, the optics were checked out. In about 2 months, it cooled down to close to minus 230 degrees Celsius. And after that, they underwent phases of telescope alignment. I'll talk about this in a moment. And then another instrument, the mid-infrared imager, started operating, then calibration. So this is the phase we are in right now. We are about 5 months after launch. This was launched in December, on 25th of December last year. And then there are a few more steps that will be done over the next month, and then science operations will begin in late June. Okay, so I said calibration and telescope alignment. So let's look at that. We have all of these hexagonal mirrors. So the first thing that was done was those mirrors were brought into position, and each of them was focused independently. So this is what the first images looked like. And then when each of those segments was focused, they got a sharp image. Then they aligned all of them together so that all of that became a single sharp image of any star. And the end result is just fantastic. Okay, so the previous space telescope, something called Spitzer, this is an image taken by Spitzer in the infrared, and at the same wavelength, here is an image taken by James Webb. So instead of this star, you see this, and you can see so many sources with so good resolution here. Especially notice here, there are two stars which are very, very close to each other, which were not even seen by this and would not have been resolved. It would have thought that this is a single source. Or if you look at this star and all these smaller bright spots around it, they appear as a single blurred blob here. So that is all coming from this sharper imaging coming from a much larger mirror, and of course more light collected by the same larger mirror. I said that the last view of James Webb was not quite the last view. That was the last good high resolution view, but you can actually see JWST from the Earth. So on Science Day this year, we undertook this nice exercise where Growth India telescope actually took a series of images of JWST, and you can see it moving against the background stars. At the same time, we also had our colleagues in Taiwan use the Lulin 1-meter optical telescope to image James Webb. And you can see in their images also JWST moving. And you can read up more about this. Based on this, you can actually figure out where James Webb is, calculate the distance and so on. And it's a nice exercise. We have released this data. So students who are listening, if you want to try it out, go to this website, to the Growth India Telescope website, and look this up. All right, so we talked about all of this. We talked about large infrared space telescope orbiting at a large distance from Earth. But all of this is really to study a whole bunch of things. So now let's look at what did JWST, what will it do? So here are the instruments that are going to be used to study it. There are a bunch of cameras that can take pictures. There are some spectrographs. Think of it like a prism, essentially, where you can split the light into its component wavelengths and allows you to study different elements that are present in the object you're looking at. And then there is something very interesting called coronagraphs, which allows you to block light from the star and see very faint planets around that star. So there are 4 instruments: a near-infrared spectrograph, a near-infrared camera, mid-infrared imaging camera, and then there is this fine guidance sensor and NIRSIS instrument. So where are these located? You have the now familiar layout of James Webb Space Telescope, and there is this box behind it, which is where all those instruments sit. Light is okay, so light is going to go in. So light will come and get reflected from these mirrors, get reflected from the secondary mirror here, and go in through this hole. And from there, it will be diverted to whatever instrument is being used at the time. So you can see the internal layout. These are the 2 larger instruments and the 2 smaller ones here. Okay, what will these instruments do? Well, the key mission goals, the first is that we wanted to search for the first galaxies that found very early in the universe. And the universe was not 13 billion years old, but maybe 1 billion years old. We also then want to take and study these galaxies, the near ones and far ones and so on, to see how galaxies have evolved over time. On a human time scale of 100 years, we think that space doesn't really change much. It's quite static. But the universe does have an age, and we want to see how the universe and all components of the universe changed over that 13 billion year age. We want to observe the star formation and really study. So stars are formed from gas and dust, which collapses under gravity, which means that when a star is formed at the center, there's still a lot of dust around it. So no optical light makes it out. And that is again where this infrared telescopes is very, very important. And then finally, we want to study planets. We want to study our own solar system, lots of objects in the solar system, moons of planets in the solar system. But we also want to catch planets around other stars, and we want to study them. We want to see what kind of atmospheres they have, if any, and whether they could actually support life at some point of time. That would be pretty cool. So the first thing that James Webb Space Telescope is going to do is what are called deep surveys. So the background that you are seeing here is the famous Hubble Ultra Deep Field image. And you can see a lot of galaxies here, but also a lot of small points here. And each of those points is also a galaxy. And this is all in optical. What James Webb Space Telescope will do is will actually be able to see galaxies that are further away. The mirror is bigger than Hubble Space Telescope, observing in the right wavelengths, which means that it will actually enable us to understand the formation of these galaxies very, very early in the history of the universe. Why do I have a Hubble image here and not an image from James Webb? That is because James Webb is still in commissioning phase. It will start observations about a month from now. So we want to know how our galaxies formed, how do they change, and not just that, how are the chemical elements distributed in the galaxy? The Big Bang mainly created hydrogen and helium. So where did other chemical elements come from? They came from stars, and how those stars were formed and died and so on. So how are these distributed through galaxies? And what happens when galaxies collide? The universe is actually quite a violent place. Okay, so what happens when galaxies collide? How do these mergers happen? And we believe that, so you may have heard about this announcement about 2 weeks ago now, where the Event Horizon Telescope team imaged the supermassive black hole at the center of our galaxy. And a few years ago, they had done that for a nearby galaxy. These supermassive black holes, we believe, form from merging of smaller black holes at the center of smaller galaxies as they collide. So all of these kind of histories also James Webb will help us understand. We want to study the life cycle of stars. I mentioned that collapsing clouds of gas and dust form stars. So what are the details of that process? And why is it that stars, what we have seen is that they're often formed in groups. So can you actually form stars that are isolated and alone, or must they always form in groups? And then when the star is formed, what causes a planetary system around it? And how is it that the planets are always in a plane? We have good hypotheses about this. We have some observations in radio which have told us things, but infrared information was lacking so far, and James Webb will give us that. And how do these stars then evolve? How do they die? And in the process, how do these elements get recycled? The air that you and I are breathing is mainly oxygen and nitrogen, and the organic compounds that make up our body, primarily carbon. All of this carbon and nitrogen and oxygen was formed inside the hearts of sun-like stars, okay, medium and low mass stars. And then in the dying phases of those stars, it was distributed through the galaxy. From older stars, those stars, the dust that was spread out from there, the sun formed from the ashes of one such older generation star, and that is why there was still carbon and oxygen and nitrogen left around in the disk that formed the planets. That is how we can exist. This is now quite a complicated procedure. This oxygen and this carbon was not made inside the sun, it was made in some other star, and it got recycled into life. That is quite amazing. So how does this happen? The details we will study with James Webb Space Telescope. And then talking about planets, are there other Earth-like planets out there? How many are there? And how many different types of planets are there? And then what is the origin and evolution of different types of objects? Why is it that outer planets are gaseous giants, inner planets are all rocky? Where there are some objects which are asteroids, some which are comets, some are icy, some are rocky? What are the details of all of these? And then when we understand this about our own solar system, we want to compare and contrast it to other solar systems to see whether the conditions there were similar or different, whether our solar system is unique or fairly common. All of these questions again is part of James Webb's study. One of the tools that we will use here is the coronagraph, which we talked about some 5-8 minutes ago. So what the coronagraph does is that at the center of this image, there is actually a very, very bright star. But the coronagraph is blocking the light from that star, which means that this faint planet around close to the star is actually seen. Now, this is an image taken from the ground-based Keck 2 telescope, but James Webb Space Telescope actually has similar coronagraphs which will allow it to image and then study planets around other stars. What it will also do is it will actually try to characterize atmospheres of planets. So what is shown here is a star, and the dotted line here shows the orbit of a planet around that star. As this planet is passing in front of the star, it blocks a little bit of light. But if you have good resolution on your streaming right now, you'll also notice that there's a faint haze around the planet, which is the atmosphere of the planet. And some of the starlight is going to pass through that atmosphere. And whatever gases are present in the atmosphere, each gas will actually absorb a characteristic wavelength. Okay, so here are some of these wavelengths marked. This is wavelength in microns, and there are bands of water and methane and carbon dioxide and ozone. So remember, methane and carbon dioxide all greenhouse gases, and that is because they are blocking infrared light which Earth is emitting. So these are signatures. These are not gases which are very easy to form and keep in the atmosphere by completely inorganic processes. So these are telltale signatures of something active happening there, which could potentially even be life. And these imprints on the spectrum are very, very small. They are 0.01% or smaller in intensity. And that is something that James Webb Space Telescope will actually be able to measure by this technique called transmission spectroscopy. Okay, and that's going to give us some very exciting results, hopefully, about these planets around other stars. Here's one case where we are actually helping one of the observations. So this is one of the early approved observations of a planetary system called HD 80606b. So this is the star. The star is called HD 80606a, and the planet is called B. And the planet actually goes in a very eccentric orbit. It's not a circular orbit. And as it comes near this, it gets very hot very quickly, because imagine this is the star. The planet comes from far out as if it was a comet, passes very close to the star, and then goes away. And the temperature goes from about 800 Kelvin to 1500 Kelvin. Surface of Earth is about 270 Kelvin for reference. So this is much hotter. But the temperature almost doubles in a period of just 6 hours. So what does it do to the atmosphere of star? It's actually going to churn it up. It's as if you have flash heated one part of the planet. And this in 6 hours over an orbit which is almost 4 months. Now, to plan the exact observations with James Webb Space Telescope, we needed to know exactly when the planet is going to pass here. So Growth India Telescope participated in a major international campaign with observers across all continents, where we imaged this star and we measured very precisely how its brightness was changing over time. And with that, we actually then helped figure out exactly when this transit is happening, which in turn will be used to schedule James Webb Space Telescope observations according to that. By the way, speaking of all of this, it wouldn't be complete without mentioning that while we are learning a lot about the universe, there are also technology spin-offs that have come as a result of JWST developments. For example, for making these precise mirrors and being able to align them and so on, they had to develop very high precision optical measurement techniques. And the companies that developed those techniques have already started using them to improve LASIK surgeries, where when you do a laser surgery, corrective surgery on your eye to correct so that you can see properly without wearing glasses. So technologies developed for James Webb Space Telescope have found an application there. Similarly, high-speed optical sensors that were necessary for calibration, they have found applications in industry immediately. they started technology development for the infrared detectors. That's the key thing for James Webb, right? So that technology development was started a couple of decades ago, and they created these extremely high-end infrared cameras, and their performance was so good that now those have become the industry standard for IR detectors. So good quality infrared detectors that are available around the world today for research or for commercial applications or for anything, all of those detectors are a spin-off of technologies that were developed for James Webb. Okay, and here's one list of innovations from James Webb Space Telescope. So while the payoff in fundamental science itself is enormous, there are also technological benefits that we are seeing in the world around us already, thanks to the development of this mission. So we will end with this. I had promised that I'll give you some links at the end of the talk. There is a lot of information about James Webb Space Telescope that is available online. I went through a lot of these websites, and I have narrowed it down to a few details which I thought would be most interesting to you. So here are 3 sites. There is a frequently asked questions on the official JWST site. I did not talk a lot about the instruments. So if you want to know more about the 4 cameras and how they work, then you should go to this site. And we are very close to starting science observations with James Webb. So if you want to keep up with the latest update, they are actually maintaining a blog which they update quite frequently. So I will close with that, and I'll leave you with this pretty picture of Growth India telescope instead of James Webb. So thank you all. It's been great meeting you. And I hope that you are excited about James Webb and the possibilities that it holds for us. So coming back to this, and we'll be happy if you have any questions, do get in touch with the organizers, and we will try to address these questions in any way that we can. Unfortunately, we cannot do a full Q&A session right now. So thanks a lot. Again, great meeting you. Have a good day. Bye.